this session, we'll look at MPI data types, derived data types. So if you have run an MPI program or written an MPI program, you should be already familiar with at least the basic data types, because every MPI function, every MPI communication function, that is, takes data type arguments in it. There's a buff, count, and data type, and then other stuff. So in the basic sense, the data type represents the type of data that you have defined in your program. So if you're sending an integer array, then the data type, you will define that as an MPI int, or whatever. If it's a Fortran program, you'll say MPI integer, so it matches the language. If it's a floating point number, you'll say MPI float or MPI real, as is the case, and so on. So the reason MPI does it this way and doesn't let you just specify your data in terms of bytes. So if you're doing a lower level type communication, so let's say you were doing programming at the network level using either sockets programming or some other lower level API, they typically don't have this concept of data types. You're supposed to specify the number of bytes in your message. So you multiply by the number of elements in your array by the size of that type. But MPI doesn't do that for a few reasons. One is that MPI is intended to run everywhere, even on a system that may be heterogeneous. So on a cluster that may be heterogeneous. So by that I mean you could have some set of nodes in your cluster that are Intel nodes, and another set of nodes that are, say, Spark nodes. So it's a different architecture, and it could have a different byte ordering in that architecture. So if you just sent your data as bytes, and you receive them as bytes, you would have to do the reordering of those bytes for it to make sense. Otherwise it won't work. You'll get completely wrong results. So on the other hand, if you specified your data type correctly in your code as whatever int or float in your whole MPI program, and you were using an MPI implementation that supports heterogeneous environments like this, that is, it can run across a heterogeneous set of nodes, then MPI will do it for you under the covers. You will get the right, because it knows what it's running on, and you will get the right data. So this used to be more commonly used in the past, I would say. 10 years ago, there were more instances of this kind of environment. Today you find less of these kinds of heterogeneous systems in this sense. The heterogeneity is within the node, where you have a CPU and a GPU or things like that. This mix of different byte ordering across nodes is not that common nowadays. So some of many of the MPI implementations may not even support it, because it's additional work to support that. So you need to check the manual, the user's guide of the MPI implementation, whether this kind of running across a heterogeneous thing works. But the MPI standard intends that it should work, and that's why it is supported. Now, those are the simple data types which everyone uses. There's another feature of MPI called derived data types that is not so commonly used, and that's what we are going to talk about. And the idea in derived data types is to allow you to specify a data layout that is not contiguous in memory. So suppose you want to communicate, to send the column of an array that is a C array, an array in the C language, which is in row major order. So the column is not contiguous, right? Each element is separated by the size of the row, and it's the other way around in Fortran, which is column major. So if you want to send a row of an array in Fortran, that is not contiguous. So how would you do that? One approach, of course, is you copy all that into you allocate a temporary buffer, copy it, send it, receive it, again and again unpack it, and so forth. And many users do that because sometimes that performs better, but we'll see, we'll see how else you can do it with MPI. But MPI allows you to describe this kind of a non-contiguous layout, send it with a simple, by creating a derived data type, send it with a single MPI function, receive it also the same way, and it does the work underneath for you. And it's quite powerful in the sense that you can call these data type construction functions recursively to describe pretty much any kind of a non-contiguous layout. So, for example, suppose you want to send these data elements that are in green and blue. So this is kind of a complicated non-contiguous layout because there's no obvious pattern in this whole thing. So you have these two elements separated by a nice stride. So this first set is relatively regular, and then you have another irregular set. So MPI allows you to do that, and the way you do that is you can create a vector type of describing these elements and an index type describing these elements, and then combine them together using a struct type to describe the whole thing, and then call an MPI send and so forth. And we'll see how we do that. This is just an example. So it's quite powerful because you can recursively call any function. As long as you know how to do it, you can do it. Of course, the more complicated it gets, the more difficult it is for the MPI implementation to do any real optimization underneath. So it may not perform in the most complicated case. It may not perform much better than if you did these by hand. That is, you copied them yourself by hand. But there are other cases where it can do better than that. The other thing you should avoid doing in this case, of course, and I think you all know this, is trying to send these elements individually, because that's the easy one. Is you see which of them are contiguous and you just send them out. But it's expensive to send small amounts of data when you want to send the whole thing. So that's why many users either use the derived data type, which takes some work, or by work I mean you need to understand how to do it in MPI, or they copy it into a single buffer and send it and unpack it. But you do want to send large amounts of data, not small. So this slide again just says why are there in basic data types. One thing to note is MPI supports all the basic data types that are defined in the language. So whatever is there in C 99 or a later version of C, all of them have their equivalents in MPI. So if you want to use int64 T, or the ones that are less not used so often, even they are defined in MPI. So if you have defined your data structure using one of those types, you will find the MPI data type to use in your MPI program. And the same with Fortran. There are many of these predefined, and you should use the correct one. Okay? So now let's look at how you can create these derived data types to describe the more complex non-contiguous layouts. So there are about 4 or 5 of these data type constructor functions that are defined, and they are in increasing order of complexity. So the simplest one is MPI type contiguous. That is used to create a contiguous type like this. So suppose you want to send this amount of data, you could create a contiguous type using this function. So one thing to note is if you just had to send this amount of data, you don't even need to create a derived data type, right? Because you can call an MPI send and use the count argument. You can say buff count data type, so you can just say the count is however many this is. It's 7, I think. If you just pass count as 7 and the data type as MPI int, if this is an integer array, it's going to send this contiguous type for you. So you don't really need this. And so this function tends to not be used so often. It is used only to create more complicated types where you need to have like the second one, where if you're creating a contiguous type of a struct and then feeding into some other function and so forth. So it tends to not be necessary so much. It's there more for completeness, because many of the other constructors also take a count argument, and that also defines a contiguous data type. So it's more for completeness than practical use. And it's relatively simple. It takes a count, it takes an input data type, and what it returns to you is an output type that is effectively defines this contiguous. So what is this output parameter in MPI? So it is what is called an opaque object in MPI. So it gives you something that is of this type, MPI data type, which is defined in the MPI.h file. To you it means nothing, but to MPI it is a handle to an internal data structure that effectively defines this type. And by defines this type, I mean to MPI it tells MPI what the layout of this data is. Okay, so this is the very simplest type. I'm just going to go ahead to the next one, which is more interesting, and then I'll stop to see if you have questions at this point. So this is the second of the data type creator functions, and this is quite used quite often. So suppose you have some regular strided data, which is like the column of an array that is in row major order. That is a nicely strided data with a uniform stride. The stride is the size of each row. That you can describe by using a vector type, and it allows you to have not just a stride, but you can have blocks of data that are separated by a stride. If you're sending a row, you don't really have blocks of data. I mean, if you're sending a column in a row major order, you don't have it's just a single element with a stride. But in general, you could have multiple. So the way this is defined is there is a count parameter, which is the number of blocks in this vector. The block length is the number of elements in each block. So here it is 2. The stride is defined as the number of elements between the start of the first block and the start of the second block. So it's 3 in this case. And then you pass the old type, which if this was, each element was an integer, you say MPI int. And what you get back from the data from the function is a new data type, which represents this kind of layout, right? One more thing to note is, and we'll get to that later, is after calling this function, you need to call one more function called an MPI type commit before you can use this data type in a communication functions. And we'll get to that. You don't need to worry about it right now. So this just shows you how you would create a vector. Now, you can create a vector of a more complicated data type as well, because the type that you pass as the old type here need not be a simple basic data type. It could be any complicated type. So suppose you want to create a vector of these kinds of these sets of data for which you have defined a struct data type, which we'll see much later. You can call an MPI type vector with the right set of parameters with MPI's this struct type as the old type, and then you'll get a new vector, which is a more complicated vector, but it's still a vector of uniformly strided blocks. Is this clear? Any questions? So what you're doing here is you're not moving any data. You're just describing a data layout to MPI, and typically you'll do it once and then use it often. That is, you create this vector type and then do many sends and receives using this vector type, because it's a little expensive. It's not very expensive, but it can be a little expensive to create these types, because once you call the function, MPI tries to understand what it means. What is a vector type, or what is the data type being passed. So you don't do it before every communication function. You do it once and then reuse it, as long as your layout doesn't change. Your data can change. What you're describing doesn't change. Is it clear how you would use it and when you would use it?
So how I would know that there is a stride between ununiform stride between the structure?
Well, that's your program, right? That's the logic in your program. Your data is laid out in some way, and you want to send some part of it. That's because of your program's logic, and you know that it's right. So, and a common example, as I said, is a column of a row major array, or suppose you had a 3D array and you had to send some part of it. That would have some kind of a regular stride in there. That's an example. Okay, so this is MPI type vector. The next one is very similar to MPI type vector, and the only difference is in the vector type, the stride between the first block and the second block is which is this parameter is defined in units of the old type. So if this old type was MPI int, here you would pass stride as 3, and this function would know that there are 3 ints between the starts of these two blocks. The next function makes it a little more general, and the stride here is not defined in terms of the number of old types. It is in bytes. So it could be a fraction or something in between a unit of a type. So that's the only difference, and they call it it's called MPI H vector. And this parameter, which was passed as an integer, it was an integer parameter, int stride in the previous case, is defined to be as MPI A int. So are you familiar with this type called MPI A int? Have you used it any time? What is an A int? Does anyone know what's an A int in MPI? Because there are several MPI functions that either take a parameter as MPI A int or return a value that is of size MPI A int. So the A refers to A int refers to an address-sized integer. So it is an integer that is large enough to describe any address on your systems. So if you're running on a node that has a 64-bit address space, MPI will define this type to be 64-bit. You don't need to worry about it, because the same code has to run on different systems. So on a system where it is 32-bit address space, which is which are not common nowadays, but they might still be there, MPI will internally define that as, in the header file, as a 32-bit integer. So since you're passing the number of bytes here and not the number of integers, this is just defined as a address-sized quantity, and that's the only difference. So now your spacing between the blocks need not be in units of the old type. It could be something in between that. So it's more general. That's all. And I think H stands for heterogeneous. This is from the old MPI 1 days, and the name is slightly different. So this is called MPI type vector, and this one is called MPI type create H vector. So the reason that happened was there was an MPI type H vector in the old MPI 1, but its Fortran bindings had a problem in the sense that they were using the old style. They were not large enough to cover the large address spaces. So it got fixed in MPI 2 long time ago, but MPI doesn't just change function parameters because it doesn't want to break old codes. It creates a new function with a new name where the interface is fixed. So that's why there is the new function MPI type, and they called it MPI type create H vector, just to fix the Fortran binding. The C binding didn't change, and this has been there since MPI 2, which is 1997. So it's been there for a long time. And there are a few other functions like this which have slightly different names, mainly to fix the old Fortran bindings. Any questions on that? No, this is relatively simple, I hope. The next type, so now we are moving from the easy to the little more complex. So we did the contiguous, we did vector. So the next thing is something that doesn't have a uniform stride. The blocks are not strided uniformly. So then how would you describe it? So if they are not uniformly strided, then you have to pass, the user has to pass an array with each of those strides in there. And that's what this does. And it's called an indexed type, because that's what you're effectively passing. So suppose you have to send this kind of data, the green elements in this array. So the strides are not uniform here. This is a gap of 3. This is a gap of 2. Again, a gap of 4 or whatever. It's not uniform. So for that, you call this function where now you have to pass two. The count is the same. That's the number of blocks. There are 2 sets of arrays here. The first one is the array of block lengths. So there is another generality. The block length is also not uniform. Here it is 1, 1. Here it's 2, 1, 2, 1, and so forth. And the array of displacements is the gap between these blocks. That is also not uniform. So that is also passed as an array. And then you pass the old type, and what MPI returns to you is a new type describing this data. So the way you would fill these 2 arrays is the block length would be 1, 1, 2, 1, 2, 1, and the displacements would be whatever are the gaps here. So it's more general. You have to pass exactly what the sizes are and what the displacements are, and then go from there. And similarly, there is a h-indexed function. It's the same thing. The difference between vector and h-vector was that the stride was in h-vector, the stride was in bytes, and similarly in the h-indexed, the array of displacements is of type MPI int, because you pass it in bytes. Now, MPI, I think it was an MPI 2.2, added another function that instead of passing an array of block lengths, if you have a uniform block length, you just pass it as one element, and only the displacements need to be passed as an array. So this is an example where you have a non-uniform stride, but you have a uniform block length. So if you use the old function, the MPI type create, I'm going in the wrong direction, indexed, you would simply have to allocate a block length array to pass all values being the same. And that's a waste of memory. So that's why this new function was added. So you'll see MPI has many functions in there. Yeah, go ahead.
Yeah, I was just wondering, these arrays that are being used here, are these copied over internally, or does it just use the values of the arrays when you use the data type?
These are copied over internally. So once the function is called, the user can free those arrays. Yeah.
Can the old type be another derived type?
Yes. That's what, as I showed some examples earlier, the old type could be any complicated derived data type. And that's why you can define pretty much anything using this method, because there is no end to what you can do. You can recursively call these functions any number of times to describe a very complicated layout. Yeah?
So new type is just like a unique handle to what this configuration?
Yes. So the new type doesn't make sense to the user. It's just you can think of it as a pointer or some handle to an internal table, internal data structure in the MPI implementation that effectively MPI stores this information in some way that it understands, or that it can use when you do a communication. So why are you doing all this is you're going to call some communication function later and pass that handle to MPI, and MPI will look up that handle and know what data to send. Yeah?
Can I query if a particular data type is already registered?
Can you query what?
Can I query if a particular derived type is registered in the system?
Is registered. By registered, do you mean the type commit has been called?
Or whatever the phrase.
Is it committed or not? Is there a function to detect whether it's committed or not, or you can just call it? You can call it twice. I mean, if you don't know, or that case doesn't occur. Can you call MPI type commit twice, or?
I'm not sure. That might give you an error about committing a committed type.
Right. So if you're in a library,
You could set errors return and try to commit.
right. Or you can tell the user that you always have to pass committed types. So I don't think there is a way to query whether a type is, unless I'm missing if there is an MPI type is committed function or something like that. But in other cases, there are functions like these to check various things at MPI. I'll just need to look up if there is such a function. Yeah.
I just looked it up. If it's already committed, it does nothing.
Okay, good. So at least it won't give an error in that case. Yeah.
Return pointer should point to something, right? Like the new type.
Yes.
Originally null, right? So
It's originally a null. It returns.
it has a value.
It has a value, and that value to you means nothing because it points to something internal in an MPI implementation. The question was, as I said earlier, in addition to these, just once you're done calling these functions, you have to do one more step called MPI type commit, which I'll get to later, where you're telling the MPI implementation that I am done defining my data, this data type at least, because otherwise you could recursively call many functions with it. So what you're saying with MPI type commit, okay, I'm done describing my layout with this data type, and that gives the implementation a chance to kind of optimize the internal representation of that data type so that it can easily look it up when you're doing communication and do that part efficiently. So the whole goal of all this is to do that communication efficiently at the end. So what he was asking is, can you check whether a type has been, because if you don't call commit, that's an error. If you just pass this output directly to an MPI send, you'll get an error saying it's an uncommitted type. That means you didn't call that type commit function. Yeah.
Is there some way to assert at the programmer level that two MPI types are the same or not? Is it possible to do something?
By assert, you mean to inform in the MPI implementation, or?
Yeah. So inform or like use that for a program.
Well, if they are the same, you could just use the same handle in both cases, right?
So if I define two index types,
Yeah.
I want to say that they are the same as in, I cannot use these for any kind of programmer logic. So that might.
So if they are the same, why are you creating them twice? If they are the same, you can create them just one and use that in any number of functions.
Possible case might be two different parts of the code, same libraries, they feel like the same.
Okay. Yeah, I don't think there is a way to tell MPI that these two are the same. It might internally, it might realize that, because it'll do the same thing twice. If you call MPI h index with the same parameters twice, it'll create two different internal structures and give you two different handles to the same thing, I think. Yeah?
If I use a vector example to send the columns of a matrix,
Yeah.
Instead of sending a vector, if I hand back it, then lose the opportunity for overlapping communication with computation. But what other kind of optimization is done by using vectors inside your iSend as far as extracting the data is concerned?
Right. So on modern networks, there might be some features available that you can point directly to non-contiguous data. So you could so the MPI implementation can not on your laptop so much, but if it's running on a high performance interconnect, a modern interconnect on a say InfiniBand or on one of the supercomputers, those networks have more features than just the bare minimum. So it could use some of them to send non-contiguous data directly, for example. So there's no minimizing copies internally. That's one optimization it can do. So the index type, and this is index block, which is just a simplification. Well, one thing I wanted to say that is, by now itself, you might have realized that MPI has many functions. What MPI could have done is just provided one function that is the most general that covers all cases. It doesn't need this gradual things. But that's not the way it is defined, and it's not considered good practice also to have one general function that is used for everything, even for the regular. So although there are many functions like this in MPI, that doesn't make it in a heavyweight or complicated, because they're all separate. Once you get the idea, you can look up what you need and use exactly what you need. And library writers who are doing more sophisticated things, they can use the more complex features as they need. If you are doing something simple, you use only the simple, the ones that you need. Okay, we did h-indexed. Okay, so now we are getting to the most general type, where it's not only the block length that is different, it's not only the stride is different, but even the basic type might be different. So you could have, so this is like if you have a struct in C which has many types in there. There could be a string, and there could be an array and other things in there. How would you describe that? So for that, this has the third, even the data type is an array of types. And so this is the most general, because any kind of data structure you can describe in this type. It's harder for the MPI implementation to optimize this one, because everything is variable here. You can have variable block lengths, variable strides, and even a different data type. But the facility exists. There are also some convenience functions that were defined in MPI 2 for communicating or doing I/O with portions of arrays. So if you have an array and you want to send a sub-array out of it, let's say it's a 3D array and you want to send a sub-array out of it, this convenience function allows you to define this sub-array in array notation. That is, you declare the size of the array, the big array, and then the starting coordinates of this subarray and the sizes in each dimension. And an MPI creates the data type for you that you can use in the communication. Now, if this function was not there, you could have used the previous functions that I described to define this layout, the vector or the indexed, and a combination of them. It won't happen in a single step. You'll have to do it recursively. But that is error prone. You'll likely make a mistake while doing that. So that's why this function exists. And it just, it's in terms of, it's in the array notation. So it's a number of dimensions, the sizes of the big array, then the sizes of the subarray that you want to send, and then the starting coordinates of this first element. And the order is whether this is a row major or column major ordering for this storage. And then you pass the old type, which is the type of each element. And what you get out of it is a data type that will describe it. And this you can use for any number of dimensions. There is no restriction. So you can do 4, 5, whatever you want. If you did it by hand, it's likely to be error prone. There is another array constructor which I would discourage you from using because it has some restrictions, and so it's the MPI type create D array, and it assumes a data distribution among processes that was defined in the high performance Fortran. So when MPI was in the 1990s and early 2000s, high performance Fortran still existed. It's no longer used that much. And that was a language where you could define a global array and define its distribution as a block distribution or a cyclic or a block cyclic. And this one assumes that very definition to describe the layout. So unless your program matches that specific distribution, it's likely to define the wrong layout. So I'd say just it's good to know about it, but don't use it unless you really know that it matches your program. There are a few other things. So there's something called MPI bottom, which is used to, which indicates the absolute zero address in your address space. So it's equivalent to 0 in some cases, but this is the more portable way to use it. And it's useful in the struct type. So again, unless you're using complicated types, you won't encounter this so much. There is also a way to get the address of a variable using MPI get address, and that's the more portable way to use it. That's again useful in the MPI type struct. Building struct types. So it's for more advanced use. And this is what I've been referring to, that you must commit a type before you use it. And so you can recursively create a derived data type describing a complicated layout. When you're done, you have to call MPI type commit. And what that says to MPI is, I'm done with this process. You can do some analysis now to figure out what I have specified and store some representation of that internally, so that when I do MPI communication later with this data type, you can do it efficiently. You can figure out whatever you need to figure out, because MPI has to know where the data is actually located, and you're specifying it in a different way. So that's type commit. So you do that only once, and then you call MPI communication any number of times. If you're just doing a single data type, like it's a vector type for a column, you can call MPI type vector. You get the data type, you can call MPI type commit right there, and you're done. You can start doing your communication. So whenever you're done creating your types, you call commit. Commit can be a relatively expensive operation, because that's where the MPI implementation might try to examine what this data type is and what it should do. And you should also, when you're done with your communication, that is whatever is your send receive that you needed to do with that data type, once you're done, you should free the data type, MPI type free. What it does is, whatever is the internal memory that MPI had allocated, that gets freed up when, at that stage. So that is type free. You can also duplicate a data type. So if someone asked this question, if there so this is not that you're given two types. You created a type and you want to create a duplicate of it. You can just call MPI type dupe, and it's useful in libraries and stuff. So that really is identical to the original type, there's no difference between them. If you free one, you don't free the other. It's really a second type. That doesn't mean it creates a whole set of memory for it. It could, the MPI implementation could use a reference count mechanism internally. That is, it could just bump up the reference count on that type and internally manage it. But for you, it's like a duplicate of the original type. Okay. There are other functions as well. So MPI does have functions that allow you to do packing and unpacking of data. So although I said that you don't need to do it, that is pack data from a non-contiguous buffer into a contiguous buffer and unpack it. This was there mainly for compatibility with the libraries, the message passing libraries that existed when MPI was defined. So you can call MPI pack with a derived data type to pack non-contiguous data into a contiguous buffer, and then separately call send to send it across, and similarly do an unpack on the other side. It's not encouraged anymore, because you really should just use the data type in the communication directly. Now there are other functions that are provided which are useful more for library developers, and that is, given a data type handle, how do you know what that data type represents? Because let's say a user created the data type and a library needs to know what that means. This is a library other than MPI, because MPI knows, you've called MPI functions. So there are functions called MPI type get envelope and type get contents that effectively return the set of parameters that the user had passed to the data type creator function. So you can effectively get the whole data type that the user created. So the user typically doesn't need it himself or herself. The libraries might need it. an MPI IO, the implementation of MPI IO needs it if it's separate from the MPI implementation. So that's just it's good to know that it exists. Another function that exists again is I would say it's more for advanced users. It's MPI type create resized. This function changes can change the size and extent of the data type. So it's useful, again, more for library writers than for users. I can just tell you what the basic idea here is. So the size, data types have something called a size and an extent. The size refers to the amount of actual data that it represents without any gaps. So suppose you have 10 integers, that are strided. I mean, there are lots of gaps in between. So the size of that data type would still be 10. It's the actual data, actual content in that data type. But the extent of that type is effectively the gap between the start of the first to the end of the last element, and with all the gaps in between. So that could be very large. So this function, you can take a data type and just change the values of these size and extent, which can make it, you'll wonder what that even means, but it changes the definition of some functions. So for example, when you call an MPI send with the buff count data type, what is defined is the data that is actually sent is count contiguous copies of that data type are sent one after another. So if the data is all contiguous, that it's obvious what that means. You just take the next amount of data and so forth. If it's a complex data type, then it is the contiguous is defined as you send the first count, the first data type, and the second data type is taken from effectively the extent of the original type. Now, if you have played with the extent and changed it here, that changes where the second data element gets sent from, and it changes where the third gets sent from, and so forth. So it can change your communication behavior. That's why I said it's good to know that it exists, and so you can do something very complex with this, and it has real uses for library writers, and MPI implementations also care about this, because those are the definitions that the MPI implementations used in communication. What exactly gets sent? It's all specified in the standard, but you'd probably not need to use it yourself. So it's good to just know what that is. Then, as I said, in your program, you should try to use the derived data types closer to the left side of this bullet. They are the simpler ones, easier for the MPI implementation to understand and optimize. So if your data structure can be described with a vector type, great. Use that. That's the easiest to optimize. Use the other ones only if you really cannot use that, and that's obvious. The other issue is, as some of you may know, is historically derived data types have not performed well in an MPI implementation. That is, the MPI implementations have not optimized what they could do with derived data types. So many users have discovered that. That is, they tried to use it, and it didn't perform better than them packing the data by hand and sending it and unpacking it. So they stopped using it, and many codes are there that don't use it. I think things are changing, and they've changed. There has been a lot of research on how to optimize data types in MPI. There are lots of papers that you can find on MPI data type optimization. So I think it's worth trying, at least for the vector and index type. The struct gets a little more difficult to optimize. So that's also something to bear in mind. So I think that's the last slide on data types. Any questions so far before we move to collective communication?
Idea on top of your head of how much gain can we get from if data type will be useful for an experiment from a project you work?
You should be able to get it depends on the type, and so one is the correctness also. This can do it. You want to minimize user error, so this can do things correctly. You can get 10-20% gain depending on the implementation. Some cases it might even be worse, so that you need to experiment with that. And it's also, you can also apply pressure on the MPI implementations that, hey, I'm doing this. When I use your data type version, it performs worse than my manual. And the more they hear that story, the more they will work on it. That means that's the vendor MPIs as well as the freely available MPIs. They do listen to users. So it's sometimes a chicken and egg problem. If the users don't use it, they don't bother to tune it, and vice versa. Yeah.
So in the MPI type index,
yeah,
the displacements be non-increasing, the non-monotonic?
Yes, a MPI type index they can, yes. But if you use it for MPI file I/O, then one of the file I/O functions has a restriction, but the type index doesn't have a restriction. So you can go back and forth in that. That's a good point you raise. Yeah.
But for all the communication, it's fine.
Yes, the communication will happen in the order that the number specifies. So if they go this way and again go back, the communication will happen in that crazy order. So that's why I say you can do anything with MPI because it allows this kind of stuff. Yeah.